Well, hello, cohort A. I hope you are having fun on this beautiful rainy day here in Ottawa. It's raining, so it must be time for cohort B to be here. But anyway, listen, we have a lot to talk about, so I'm going to get right to it. Back to electricity. We're done the chemistry. I haven't really marked the chemistry yet, but I'll get to it as soon as I can. Let's talk about electricity, though. So the story so far, the last thing we talked about, just to jog your memory because it's been a while, we talked about electric current, and we talked about how you can make electrons flow in a wire using a device called, if you remember, this is a voltaic cell, okay, invented by Alessandro Volta, and it produces a type of current that we see in electric circuits, okay, and we talked about primary and secondary cells. A primary cell is not rechargeable, okay, so it's used once and then discarded once all the chemicals are used up that produce the electric current. Secondary cells can be recharged. The reactions can be reversed, and by plugging electricity into them. And so your phone batteries and stuff like that will use that, so that they can be recharged many times. Okay, and we talked about what electric current looks like in a wire. So let's just look at that just briefly one more time. So here we have electron flow, and you can see the switch opening and closing as the electrons flow through the wire here. So here we have the electrons flowing from negative to positive. We call that's correct, it's electron flow. Okay, and what the battery does is provides the push that pushes the electrons through the wire. The wire is always neutral. Okay, that's a good thing to know. The wire is always neutral. What's happening is just the electrons are being pushed, okay, and being caused to drift through the wire. And they have to be able to form a complete circuit. They have to have somewhere to flow to. They won't pour out of the end of a wire if the wire is cut or something like that. They can't do that. They have to have pressure behind them to jump off the wire. And there's just not enough pressure in a wire like this, in a battery-powered system like this, to push them off the end of a wire, okay, and into the ground or something. They have to have somewhere to go. So in this case, they go back to the battery, okay? So we call this a complete circuit as they make their way around the path through the light bulb that you see there. All right, so did you know that the name of a famous band, okay, was named after the two kinds of electric current? Okay, and the band is, drum roll, AC/DC. AC stands for alternating current. DC stands for direct current. So let's talk about direct current first, since it's the same as the battery. The deal with electric current, that's direct current, is electrons flow in the same direction all the time is the key thing. For batteries, this means from the negative terminal, from the anode, okay, to the cathode, which is the positive terminal. And that's how electrons flow, but it's always in the same direction. Now, I do want to point out is thanks to Benjamin Franklin, we usually use conventional current, which has everything backwards, and it flows from, conventional current will flow from positive to negative. But most textbooks are printed that way, not because anyone thinks it's really like that, just because we just sort of are just going with the convention of history. And that's how Franklin labeled it, and so we all know it's the other way. But most textbooks still label it that way, I guess, if you want to think of it this way, in honor of him, okay? All right, alternating current. Alternating current is not like direct current in that the electrons actually alternate the direction that they're traveling in the wire, okay? Now, batteries don't produce alternating current, but turbines. Okay, so let me just highlight some of the important things. Here, the electrons are reversing the direction of flow on a repeating cycle. So what they're doing is they're just vibrating back and forth, alternating their direction. And its turbines, which is a different kind of generator, can be designed to produce alternating current. Okay, so there you go. DC, direct current, the current flows the same way all the time. AC is alternating current, and that's where they go back and forth. Now I've got a little animation of those two types of current for you here. And so here you can see the difference between DC and AC. Notice the DC, they've got Benjamin Franklin's rule with the conventional current there, going from plus to minus. And alternating current, notice how it goes back and forth. Alternating directions, okay? And that little blue circle with the wavy line in it represents an alternating current source. For some reason it's zooming in. Let me zoom out for you here. Okay, so AC versus DC. You see the difference. See how in DC the electrons flow the same way all the time? There's a little stuttering in the video, I'm not sure why. And then AC, they alternate direction. Okay, so there you go. That's the difference between AC and DC. Now, we should talk about other methods for generating electricity other than batteries, okay? So, other methods for generating electricity other than batteries. So we're not talking about batteries now. Batteries is not how we produce electricity on a large scale. What we use for that normally, and I've got a demonstration I can show you tomorrow on this. This is what you're seeing here is a schematic of a turbine. And I'll show you the animation tomorrow. This spins. Okay, there's a little coil in there that spins. It's a rotating armature. And these blue and red objects that you're seeing here are actually magnets. Okay, we discovered about 150 years ago or so, like if you want a discovery that changed the world as we know it, it's this, that if you take a coil and you spin it in the presence of a magnetic field like this, electricity will be induced in the coil. So it'll produce electricity, becomes a generator. Okay, this here is a meter used to measure the electricity, but you could put a light bulb there, right? If you wanted to power the light bulb. These rings that you see are just to allow the rotating system to brush against a conductor. So there's a brush that brushes against it. We don't want our wires getting all twisted up. So we use these rotating rings with a metal brush that touches them. And the brush will carry the electricity to your stationary light bulb or whatever it is you're powering with your generator. And guys, this is the primary way that we generate electricity in society today. We spin turbines, okay? And when they spin, they produce electricity. And this is a basic design, the first diagram. Now here is a hydro generating station. So this is where you use water to make the turbine spin. You need some way of forcing them to spin. If you can force them to spin, they produce electricity, okay? So you can use water to do that. You can use wind to do that. So here you can see the wind energy, all these towers, and those towers, I've seen these up close, okay, some of these towers, and what they do is they're designed to simply spin when the wind passes over them, and that produces electricity in the process. So if you go to Prince Edward Island, which they get a lot of wind out there in the open water all around them, well, then there you go. You're going to get a nice source of pretty well continuous electric power if it's windy all the time. Here in Ottawa, sometimes it's windy, sometimes it isn't. Wouldn't be very useful, as useful here. But if you get places that have consistently pretty strong and moderate winds, that's excellent. And out in the ocean, close to the shorelines, some of those places are windy basically all the time. So it's perfect. Okay, there are other ways of generating electricity. Solar cells. Solar panels have no moving parts. This one is in this huge array of solar panels that you're seeing here, I think is one from Egypt. Okay. Now if you live in the desert, you've got ideal conditions for solar power there. It's sunny pretty much all the time. Okay, you don't have to worry about snow accumulating on the panels or anything like that. Maybe they get a little dusty. Maybe you got to clean them off every once in a while. But honestly, they'll produce for you, this one's enormous, this huge field of solar panels. Yeah, that'll produce power for 20, 30, 40 years with very little maintenance because there's no moving parts. Okay, so literally the sunlight shines on the panel and produces electricity. Okay, it's pretty great technology. You make solar panels from sand, basically, but you have to manufacture silicon wafer out of it, so you know it's a little more complicated. You know, you will get some waste products involved, but yeah, overall zero greenhouse gas emissions once you've built the panel and it's just sitting there in the sun for 40 years. So it's a really excellent source of power. I happen to have solar panels on my roof. Okay, that handsome guy in the picture is me, and these things back here are solar panels. Notice how they're covered in snow. Okay, so this was taken 1 or 2 years ago, whatever, back in November, where we had to grow beards. That was the thing. My wife hated this. You don't see my eyes there, I guess, but yeah, that's me. You can see how my the color of my beard and my hair are kind of on the orange side. That's what they look like in sunlight, at least. Okay, but yeah, and my solar panels, I've got 40 of these panels on my roof, and they produce about 12,000 watts of power when they're in full sun. But I got to get up there, and there's one of the disadvantages of solar power. I've got to get up there and take the snow off when it accumulates in the wintertime. Otherwise, not just will they produce no power at all with snow on them, but also the snow, if it builds up enough, it'll slide off the panels all at once like an avalanche, and that can be dangerous. So I always try to get up there and make sure I take it down. Okay, so those are the basic methods that we use to generate electric power. Okay, so we use batteries, we could use solar panels, we could use turbines, and turbines can be spun using various means. One I didn't mention here is nuclear power. Nuclear power will spin a turbine too. What you do with the nuclear power is you create superheated steam under pressure, and then that pressurized steam will spin a turbine and create electricity for you. Just got to find ways to spin the turbine. Okay, if you want to volunteer, maybe you could run on some treadmills and stuff like that, spin our turbines for us. Like, we'll make these big giant hamster wheels for you, and you can like run on the turbines, guys, and produce electricity for us. Wouldn't that be great? You get exercise, we get electricity, everybody's happy, right? Okay, so now that we've looked at different ways we generate electricity, let's talk about how we measure electricity. So I'm going to scroll back up here. Okay, so far in our conversations, we have not discussed any numbers with electricity, any kind of math or calculations or anything like that. And what are the units that we use to describe electrical quantities? So what I'm going to do right now is I'm going to go through some of that with you. So pay careful attention here. It's going to take us a little bit to get through it. Okay, and take notes. I would be taking notes if I were you while you're listening to these online lessons. So look, how electrical quantities, let's call the lesson electrical quantities. So measuring electricity. Why do I have the metric chart here? Well, it's going to come up. Fortunately, you know this already, but just take note of the following. Kilo means 1,000, right? You can ignore most of these other units. Milli, little m for milli, means 1/1000th of something. Micro, this is going to come up, means 1,000,000th of something. Now I'll explain why these units, I'm highlighting these ones in particular. Every once in a while we measure the power consumption in a city in megawatts, for example. That means 1,000,000. Okay, so keep these numbers in mind as we move forward. So that's the metric chart. Okay, now let's talk about how we measure charge. Now some of these things I've underlined already. I'm just going to erase some of that and then I'll go through it again with you. Okay, we're going to start with how you measure charge. Okay, so charge. Charge is measured in a unit called coulombs. Okay, so this is how we measure charge. Just think of it like this, okay? Students get confused sometimes, okay? We measure your mass in a unit called kilograms, right? Well, what really is a kilogram? Okay, I could talk to you about how they define what a standard kilogram is. But a kilogram is a certain quantity of matter, right? And it has a certain weight to it, and depending on the density, it has a certain bulk to it as well. Okay, but a kilogram, that's how we measure mass. Well, coulombs is a unit, and that's how we measure charge. So I told this to the students today, just like we don't measure mass in terms of how many atoms something has, although that maybe not a completely invalid way of thinking of it. Same thing for charge. We don't measure charge by just simply counting how many excess or deficit electrons you have. okay, and saying, oh, he's got 3 extra electrons, so he has a charge of -3. It doesn't work like that because individual electrons have a very small amount of charge. So what we do is we have a much larger unit of charge called coulomb. And in fact, coulomb is a very large amount of charge. 1 electron, so just let me highlight this for you. 1 electron or proton, they carry the same amount of charge, but look how small the charge is when you measure the coulombs. It's only 1.602 times 10 to the -19 coulombs. So that is like a sort of a millionth of a trillionth of a coulomb. So it's really, really small amount of charge. Well, that's how much 1 single electron has, or 1 single proton. So together they're still neutral, but this is the official way that we measure charge. The elementary charge is the charge on the electron or the proton. You can't get any smaller charge than that. That's why we call it elementary. And we use the variable q, so this is important. We use this variable q to represent charge in a formula. Okay? So some students will say, why don't we use C for charge? And I tell them it's because we use C for too many other things in physics that we decided not to use the letter C for charge. I mean, honestly, it really doesn't matter what variable you use, but the textbooks usually have Q for charge. Okay, and sometimes we use the same letter more than once to mean 2 different things and everything, so it gets kind of confusing because we run out of letters of the alphabet, quite honestly. But anyway, for us in grade 9, easy, Q equals the charge on an object, okay? All right, now just a little note about charge. A coulomb is actually a fairly large amount of charge, okay? A coulomb. So when Isabella touched the Van de Graaff machine and her hair stood up, there was not a coulomb of charge on the Van de Graaff machine. If there was a coulomb on there and she were to touch it, it would kill her. Okay, the discharge would actually kill her. So a coulomb is actually a very dangerous amount of charge in terms of static electric charge. A lightning bolt might have 15 coulombs of charge. That's a typical lightning bolt. So 15. So that's just, that's only, 15 coulombs. So 1/15 of a lightning bolt would be 1 coulomb. And you can imagine that that could be a very deadly discharge if it were to discharge into you. The Van de Graaff machine, or a balloon, okay, charged by friction, or the Van de Graaff generator, might carry only this much charge, okay? 1/millionth or 2 millionths of a coulomb. So this 2 times 10 to the -6 coulombs, that's just a millionth. So take a 1 coulomb charge and divide it by 1,000,000, okay? And then that's how much just 1/millionth of a coulomb might be on, or 2 millionths in this case, on the balloon or the Van de Graaff machine. And that's enough to make Isabella's hair stand up. It's not enough to hurt her in any way though, okay? So we use remember your metric system, the 1/millionth is this symbol right here, micro, it's 10 to the -6. So typically charges on balloons and Van de Graaff machines are measured in microcoulombs, okay, 10 to the -6 coulombs. Don't forget the metric system, okay? Anyway, when you rub a balloon on your head, you get millionths of a coulomb. That's typical. A lightning bolt, as I say, might carry 15 coulombs of charge. If the Van de Graaff had 1 coulomb of charge on it, the discharge would stop your heart, okay? And that's, if you're not sure what that means, it means death. That means death. You do not want anything to stop your heart, unless, of course, you're having a heart attack. Then we actually give you a shock like that, and we're hoping it resets your heart. Okay, that's called the defibrillator machine. We'll talk about that later. Okay, not later today, but in another lesson. All right, what about current? Well, current is the flow of charge. It's the flow of charge. We've been talking about current, right? But what we haven't talked about is how you measure, okay, current. Current is measured in coulombs per second. So think of charge as coulombs, right? So let's pretend for a second that you, students, each one of you is a coulomb. Okay, if you're, say, walking down the street or walking into my room, opening the door and walking in, we can measure the rate that you do that by just taking the number of students and dividing by time. Okay, and then you get so many students per second walking by. Well, you measure electric current this way, but it's not students per second, it's coulombs. And coulomb is a charge, right? It's a quantity of charge. Coulombs per second, that is what the unit we use to measure current. So it's measured in coulombs per second. Now, we have in history, so coulombs per second is the unit, but in history what we've done sometimes is we've renamed some of the units after famous scientists. So guys that contributed to electricity include this guy named Ampere. And so 1 coulomb per second we now just say is 1 ampere, or for short 1 amp. From now on I'm just going to say 1, like A for amps, capital A. And by the way, if you're wondering how much an amp is, 1 amp is enough to potentially kill a human. Okay? You know, there's a variety of factors, but 1 amp. Now, if you were to touch if you were to touch a wire into a plug or something, okay, and it gave you a shock, you would very likely not get an amp from that, even though it could give you maybe up to 15 amps before you trip the circuit breaker. But the thing is you have resistance in your body, so your body will not draw that kind of current from the power source. If we increase the voltage, though, you're in trouble. Okay, so that's one reason why we respect high voltage warning signs and we don't touch things or go near something that has that kind of warning on it. All right, so look, we use the letter I. Whoops, I didn't mean to cross that out. We use the letter I to represent current, okay, mathematically. So the variable we use for current is I. Again, we don't use C. We don't use C. We use I. That's normal in the textbooks. And Q is charge divided by time, right? So if you're trying to calculate current, you take the amount of charge that flows through the wire, divide by time, it flows past a point in the wire, divide by the time it takes. And so Q is charge in coulombs, T is time in seconds, and the current will be measured in amps. And I did an example here. Let's say you had a wire and you had your measuring device that measured 5 coulombs of charge that pass a point in the wire in 10 seconds. Well, to find the current, you would just go 5 divided by 10 is 0.5 amps. Okay, and that's it. It'd be like 5 students entering the room, okay, in 10 seconds. What's the flow of students? Well, it would be 0.5 students per second. In other words, it takes 1 student 2 seconds, okay, to make it through the door entirely. So half a student enters the door per second. Of course, you can't just get half a student. What it means is you get a whole student, but it would take 2 seconds for that to happen. Okay? So only half of you would sort of enter the door, and the other half would come in the next second. All right, so that's how you measure current. Okay, now what about work and energy? So this one is not necessarily related only to electricity. Current certainly is. But work and energy is really a generic term in physics, and work is defined. You should have learned this in elementary school at some point, or grade 7 and 8, I don't know. But it is the product of force and displacement. Okay? I know my son did this, I think, in grade 7. Or no, grade 8. Grade 8, I correct myself, grade 8. So work, and I know a lot of you are not familiar with working because, you know, you're kind of slackers and lazy. That's okay, though. I mean, you're addicted to your phones. I get it, okay? But this is how you do real work, my friends. You exert a force on something through a distance while it's moving, okay? So we're going to use W for work, F for force, and D for distance. So force is measured in a unit called newtons. Let me write that out. In honor, of course, of Isaac Newton. Okay. D is distance in meters. Whoops. Distance in meters. So that's what distance, we're going to use the letter D for distance. And the units of work then would be newtons times meters. But again, we named this one after another scientist called James Joule. And 1 newton times 1 meter is 1 joule of work, okay? And by the way, that'll cost you 1 joule of energy as well, okay? If you want to think of it like this, an apple weighs about the same as a Newton. Now if you take the apple, see look, I have an apple in my hand. I'll take it out of my lunch bag. So as you can see, I have an apple in my hand. See, I'll take a bite out of it. There you go. So now I'm rudely like talking with my mouth full. But I have an apple in my hand. If I take the apple and lift it up 1 meter, so if I do this, here I am, okay, holding the apple. And then, well, I guess that's not really me. I have to, like, you know, put the muscles here. Okay, so there. That's me now. Okay. And what I do is I lift this up 1 meter. Okay. If it takes 1 Newton of force, let's say I'm lifting up here with a force, my lifting force is 1 Newton. So an apple weighs about a Newton, so that's about right. So 1 joule is about the amount of work you're doing if you lift up. Imagine picking up an apple off the floor and then holding it in your hand. You've done a joule of work to do that. So that's about how much a joule is. Not very much, right? Okay. So anyway, there's a connection between energy and work because energy is the capacity to do work. So, you know, how am I able to lift an apple in the first place? Well, my body contains energy. And that's what allows me to do this work. Okay, now the energy that's stored in my body is chemical energy from the food that I ate. Okay, so, well, also because I'm Kryptonian, it's the solar power that I absorb too that gives me my powers and everything else. But that's just between you and me, okay, shh. So anyway, whenever work is done, energy changes forms, right? So when I lift up the apple, the chemical energy in my body is being turned into a type of mechanical energy that we call gravitational potential. I'm lifting it up against gravity. So that takes work. To do that, to lift anything up takes work. And you're using, whenever you do work, you're using the chemical energy in your body to create another form of energy. Okay, so you're transforming. Your body takes one type of energy and transforms it into another. And your body's a machine that's constantly doing this. In fact, even when you're just sitting there on your phone because you're addicted, so you're just sitting addicted to your phone, not moving around too much, your body's still producing heat all the time. We call it waste heat. And it does that at a rate of about 60 joules per second, believe it or not. Okay, somewhere around there. I think. I gotta maybe verify that number, so we'll treat that as like, let me verify by looking it up, but I think it's around 60 joules per second for the human body. All right, so the formula for work I already told you is force times distance, and I already told you about the units. And as long as you understand that you can use the words work and energy interchangeably, because energy is the capacity to do the work. So when you do work, both energy and work are measured in joules. And so whenever you do work, you're using some energy to do that. Okay, now that you know what energy is, you know what work is, you know what charge is measured in, okay, now I can finally tell you what voltage is. So voltage is defined as the energy carried per unit charge. So let's pretend, again, that the students are charges. And let's say you ate your breakfast this morning and you now have energy inside you. Well, the energy per student is kind of like what we mean by voltage. Okay? Now, with electricity, we're not talking about students, we're talking about charges, and in this case we mean coulombs of charge, because that's how we measure charge. So the logical unit would be joules for energy divided by coulombs, right? So joules per coulomb. However, we named this one after the guy who invented the battery. So we say 1 joule per coulomb is the same as 1 volt, and from now on I'm just going to use a capital V for volts. So 1 joule per coulomb of charge. So imagine if you ate, like, let's say a joule was like a teaspoon of sugar. Okay, so you had a teaspoon of sugar for breakfast, very unhealthy, by the way. Okay, let's say you had a teaspoon of sugar, for breakfast. And so you have 1 teaspoon per student. That's like 1 volt, okay? But if you had 5 teaspoons of sugar for breakfast, then you have 5 volts of energy per student if you ate that much sugar. So it's just how much energy you contain per charge, okay? So this is the formula. Voltage equals energy divided by charge. See, that's true by definition, right? It's the energy per charge. So energy or work is measured in joules, as you know. Charge is measured in coulombs. And so the units are joules per coulomb or volts. That's it. All right, one last thing, and I know I'm already at the 30-minute mark in this video, so I won't take too much longer. So one last thing is power. Now, as you know, in my classroom, I have all the power. And, I get to tell you what to do and you have to do it. That's really fun for me, okay, to have that kind of power. And that's my favorite part of teaching is, torturing my students with these tasks, and the assignments and everything else. It's extremely enjoyable. But we're not talking about, like, political power. We're not talking about that kind of power. We're talking about power in physics here, right, in electricity, okay? So what is the definition of power for just in general? Well, it means the rate that work is done. Okay, the rate that work is done. So let's say you're climbing the stairs. Well, it's pretty easy for us to calculate how much energy you use when you climb a flight of stairs. It's a simple calculation. We do it in grade 11 physics. Okay, so you're working against gravity. Now, to find out how much power your body is using during this time, you would divide the amount of work you're doing by time, because it's the rate that you're doing work. Okay, so now power is measured, therefore, in joules per second. Makes sense. Energy is in joules. Time is in seconds. And 1 joule per second, again, we named this after a famous scientist, is 1 watt of power. Okay, and from now on, I'll just use a capital W as a unit for power, which is watts. So there's a formula for this. The formula for power is energy divided by time, okay? The units of power, watts, and 1 watt is the same as 1 joule per second. Okay, so there you go. Now, I just want to say one thing as a note for you, because I have an assignment for you, but we're pretty much done. But I just want to show you something. I'm going to circle this. This is the definition of voltage. This is a little summary. Voltage is energy per unit charge. Okay. This one I'm going to circle in red. This is the definition of current. Current is the flow of charging, so it's charge divided by time. And power, which I'll highlight in yellow, power is energy divided by time, right? So that's power. And how are these things connected? Well, I'm going to show you a little trick. Let's say I multiply voltage times current. So what I'm going to do, if I multiply voltage times current, I'm going to take, here, I'm going to erase this arrow. I'm going to take the definition of voltage and put it in there, take the definition of current and put it in there, and if you know your math, which I know you should know from grade 8, that if you're multiplying and dividing by charge, the charge, and I'll show you again, cancels out. Okay, oops, I erased a bracket. It cancels out. And what you're left with is simply energy over time. But that's the definition of power. So what I've just proven to you is that power is also equal to voltage times current for electrical devices. And that's it. All right, so that ends the lesson, but I do have an assignment for you, and I only want you to do this assignment today, not the textbook homework. So for tonight, only the assignment I'm about to show you, nothing from the textbook. Make sure we're clear. Nothing on the textbook for tonight. Nothing. Okay. All I want you to do is a worksheet. Okay, and I'm going to show you the worksheet right now. You're going to love this worksheet. Okay, I personally really like it. And what I did in the margin here is just a summary of everything we've done so far. Okay, so take a look. I've got 4 triangles here. The first one is for current, like the density triangle, remember that? This one is for voltage. this one is for power, and this one is for work. Okay? So, you do not, unless you're Kate, you do not have to memorize these triangles. They'll always be given to you. Okay, you just have to know how and when to use them when you're answering a question. Okay, so we've learned a lot today. We've learned the definition of current, of work and energy, voltage, power, okay? And so you've got all of this information. Now, can you use it to answer some questions? And let's take a look at the assignment, you'll see what I mean. So you've got these numbers here, and you've also got the metric system, okay, that I included with you in the notes. So here's some questions for you. Now, before we get into these questions, I just want a disclaimer. The names and stuff used in this assignment are purely fictional, and you know, any resemblance to real people is purely coincidental. Okay, it's purely coincidental. Okay, so, you know, keep that in mind. All right, so let's take a look at some of these questions, and I'm only going to do a couple of them for you, and then I would like you to try it on your own. All right, so look at question number 1. Rhiannon is forgetful, of course. Okay? When she finally pays attention, she notice finally. Yeah, that's Rhiannon for you, of course. Like I said, these are fictional characters, guys. Okay? She notices that 5 coulombs of charge passes a point in a circuit in just 2 seconds. And the question is, what is the current? Okay? So what is the current? So 5 coulombs in 2 seconds. Now you'll notice that all the questions in this whole sheet, they give you 2 pieces of information, and they ask you for a third one. So they told me 5 coulombs. Well, that's charge. That's Q. We use Q for charge, right? They also gave me 2 seconds. Well, that's time. We use a small t for time. And they're asking me for current. Well, current is I. Okay? So Q for charge, T for time, and I for current, right? So what triangle am I going to use? Well, the one with I, Q, and T in it, that's triangle number 1. So to do this question, we're going to use triangle number 1. And you can see that I've done it for you here. You're going to write the steps. So you're going to write I is equal to Q over T. Okay, so that's what I did here. I is equal to Q over T, right? And then substitute in the values in the question. So they said Q was 5. They said T was 2. And then when you 5 divided by 2 is 2.5. So the answer is 2.5. And don't forget the units. Current is measured in amps. So it's coulombs per second or amps. And that's it. Easy, right? I thought you would say so. Okay, now I want to do one more for you, and then we're done for today. Question 3. Question 3, I'm highlighting question 3 because it's you know, one of those questions where you have to use the metric system. So let's just take a look at that. Okay, and again, it's the same triangle, but you could be using any of those triangles, so I will let you figure it out. But it says here, the other Alex, so not like Zimmerman, the really annoying Alex. This is the even more annoying Alex, okay? He's timing how long it would take to deliver a massive shock to an unsuspecting but deserving Andrew. Like I said, these are all fictional characters, of course. How much time will it take? So they're asking us for T, how much time it will take for 100 coulombs, that's Q, and then here a 450 milliamp source, okay? So I should, milliamps, okay, 450 milliamps, that's I, the current, but notice it's in milliamps. So I want to go back to my metric chart here, and so I'll go back to the top of my page where I have my metric system. Milli means, I'll erase it, highlight it for you again, milli is this one, and it means 10 to the negative 3. Okay, so watch carefully how I answer this question. Let's go back to our calculations. The way I'm going to answer this question is as follows. They tell me that the charge was 100 coulombs. So I'm going to write that down. Q is 100 coulombs. They tell me that the current is 450 milliamps. Right away, I'm going to change the milliamps to regular amps by substituting, here's my milli, I'm going to substitute a 10 to the negative 3 times 10 to the negative 3 to convert it to amps. And so now this is in amps. You must do that every time. You must convert to the base unit, which means you put in the power of 10 if it's not the base unit. That goes with a metric chart. Now I can go ahead and do my calculation. So time, if you're wondering how we'll go back to our triangle. If you're solving for time, cover up the t. Okay, what am I left with when you cover up the t? Well, you're left with Q over I. So that's how you use the density triangle. That's how you use the current triangle. So I get Q over I, so now I'm going to go ahead and do Q divided by I. So that's 100 divided by this number here, 450 times 10 to the negative 3. And when you do that, you should try it in your calculator, you get 222 seconds. So it's going to take 222 seconds for Andrew to get what he deserves, right? That's it. Okay, so what I would like you to do for homework is only this sheet, okay? Now you'll notice maybe there's a few more names that you recognize in here. I don't know how this happened, guys. It's one of those things. Like, look, there's Sarah and Kate. Yeah, do we even know who these people are? Lauren Boulanger, I don't know her, but yeah, rings a bell. Sounds familiar. Okay, boulangers make bread, right? Boulangerie, isn't that a bakery in French? See, look how good I am at French. So anyway, guys, here's your assignment. There are 19 questions here. It won't take that long to do it, but please, that's your homework for tonight. So can you please do it? And then if you can't do any of these questions, please ask me tomorrow. So have a wonderful day and enjoy your assignment. I think, yeah, I think you'll find it enjoyable. I know I enjoyed making it for you. Okay, so we'll talk to you soon. Bye-bye.